Over a single shift, a nurse captures thousands of data points. They record subjective complaints of pain, objective physiological vital signs, and complex demographic histories. When this information enters a clinical research study, all of these varied human experiences are stripped of their physical context and translated into identical-looking digital numbers in a database. This creates a severe methodological trap. Just because a clinical observation is recorded as a digit doesn't mean it possesses the exact mathematical logic as a standard number in an equation. Consider the number 2. In a demographic database, a 2 might represent a patient's gender code, distinguishing them from a 1. In a completely different column, a 2 might represent a patient's subjective score on a mild pain scale. In a third column, that same 2 might represent a patient's physical length of stay in the hospital, exactly 48 hours. Typographically, these 2s look identical. But treating a demographic category code with the same mathematical logic as a measure of time produces invalid statistical analysis. The resulting conclusions will actively mislead clinical practice. Before researchers can select a valid statistical test, they must properly identify the mathematical DNA of their data. Statisticians solve this problem using the scales of measurement. This strict classification system defines which mathematical operations are valid for a given set of numbers. This diagram shows the 4 steps of the measurement staircase, following the acronym NOIR: nominal, ordinal, interval, and ratio. The hierarchy functions cumulatively. Moving upward, each step inherits the rules below it. The lowest step restricts to basic counting. Higher steps validate advanced arithmetic. Clinical tools pull data from all 4 levels of this staircase. Misidentifying the level of a specific measurement tool is a fatal error in study design that ruins the data before the analysis even begins. Navigating this staircase correctly is the absolute minimum requirement to translate raw patient care observations into rigorous scientific evidence. The first and weakest level of measurement is nominal data. It is used purely for naming, labeling, or classifying observations. Common clinical examples of nominal variables include a patient's gender, blood type, ethnicity, or medical diagnosis. Nominal data must follow 2 strict rules. First, categories must be mutually exclusive, meaning a patient fits into only one category. Second, they must be exhaustive, meaning every single patient fits into at least one category. Researchers often assign numbers to nominal categories, like assigning a 1 for male and a 2 for female. These numbers are purely digital barcodes designed to make database sorting easier. They possess absolutely no inherent order or quantitative magnitude. You cannot add, subtract, or average these barcodes together. Because arithmetic is banned at this level, the only valid statistical analysis for nominal data involves counting frequencies and calculating percentages. Nominal data is highly effective for proving group membership, but it is entirely incapable of measuring the intensity or magnitude of a clinical phenomenon. The second step is ordinal data. It inherits the rigid categorization of nominal data, but it introduces a critical new property: rank. Looking closely at this ordinal measure section, you can see how variables are arranged in a clear ascending order of magnitude, moving from a mild 1 to a moderate 2 and up to a severe 3. But notice the limitation. We know severe is definitively worse than mild. What we do not know is exactly how much worse. The exact quantitative difference between the ranks is undefined. This creates the pain scale paradox. If a patient reports a pain score of 8 and another reports a 4, it is mathematically illegal to claim the first patient is experiencing exactly twice the physical agony of the second. Another frequent ordinal variable in research is socioeconomic status, categorized simply as lower, middle, and upper class. The most widely used ordinal tool in nursing is the 5-point Likert scale. A Likert scale measures subjective attitudes by asking patients to rank their response from strongly disagree to strongly agree. Because the true distance between agree and strongly agree is unknown and uneven, operations like true addition, subtraction, and calculating a precise mean are technically invalid. This creates a persistent methodological tension. Nursing researchers frequently bend these rules when analyzing multi-item Likert scales, treating the sums as higher-level data to justify using stronger statistical tests. Ultimately, ordinal data succeeds at providing relative positioning, identifying who is worse or better, but it fails to provide precise, measurable quantitative distance. The third step is interval data. It inherits rank from the ordinal level, but finally introduces uniform, numerically equal distances between values. This guarantee of equal spacing is a major upgrade. It authorizes researchers to meaningfully add and subtract data points. This Celsius thermometer graphic is the classic example of interval measurement. The jump from 20 degrees to 30 degrees covers the exact same physical distance as the jump from 30 degrees to 40 degrees. However, interval data still has a defining limitation. It lacks a true absolute 0 point. A measurement of 0 degrees Celsius does not signify the complete absence of temperature or kinetic energy. It is merely an arbitrary freezing point set on a continuous scale. The property being measured still exists in the negative numbers. Because there is no absolute starting point, calculating ratios remains banned. It is mathematically incorrect to claim that 40 degrees Celsius is twice as hot as 20 degrees Celsius. In research, when investigators sum the individual scores of a 20-question ordinal depression survey to create a total score, they generally analyze that final total as interval data. Interval data empowers researchers to measure exact, uniform differences between patients, but it still prevents them from calculating absolute proportional multipliers. The absolute pinnacle of the measurement hierarchy is ratio data. It possesses equal intervals plus the critical addition of an absolute 0 point. Here, an absolute 0 represents the complete physical absence of the property being measured. Negative numbers are impossible. Objective physiological markers dominate this category in nursing research. Patient weight, blood pressure, heart rate, and length of hospital stay are all ratio variables. Because a true 0 exists, absolute ratio comparisons are finally mathematically valid. Looking at this medical scale, an 80-kilogram patient weighs exactly twice as much as a 40-kilogram patient. Ratio data is fully continuous. It supports the entire spectrum of mathematical operations, including precise multiplication and division. Capturing clinical phenomena at the ratio level is the ultimate goal of quantitative design. It yields the most robust, irrefutable evidence possible. So, how does a variable's position on this NOIR staircase dictate the actual research tests a clinical investigator is allowed to run? The answer comes down to statistical power. Statistical power is the innate mathematical ability of a specific analysis technique to detect true, significant differences hidden within clinical data. Nominal and ordinal data restrict researchers. Lacking continuous equal distances, these lower levels are diverted into non-parametric tests, like chi-square analysis. By contrast, interval and ratio data satisfy the strict mathematical requirements for highly sensitive parametric statistics, calculating more precise models of clinical reality. Parametric tests allow researchers to calculate true statistical means, standard deviations, and complex correlations across massive sample sizes. If a researcher forces a parametric test onto weak nominal data, the software outputs an answer, but the resulting conclusions will be mathematically invalid. The NOIR hierarchy provides the structural grammar required to produce, evaluate, and trust evidence-based nursing practice.